Section 7.4, Ionization Energy. The ease with which electrons can be removed from an atom or ion has a major impact on chemical behavior. The ionization energy of an atom or ion is the minimum energy required to remove an electron from the ground state of the isolated gaseous atom or ion. The first ionization energy, I1, is the energy needed to remove the first electron from a neutral atom. For example, the first ionization energy for the sodium atom is the energy required to process sodium going to sodium ion plus an electron. The second ionization energy, I2, is the energy needed to remove the second electron and so forth, for successive removals of additional electrons. Thus, I2 for the sodium atom is the energy associated with turning sodium cation into sodium 2 plus an electron. The greater the ionization energy, the more difficult it is to remove an electron. Periodic trends in the first ionization energies. We have seen that the ionization energy for a given element increases as we remove successive electrons. What trends do we observe in ionization energies as we move from one element to another in the periodic table? Figure 711 shows a graph of I1 versus atomic number for the first 54 elements. The important trends are as follows. Number 1. Within a row or a period of the table, I1 generally increases with the atomic number. The alkali metals show the lowest ionization energy in each row, and the noble gases the highest. There's a slight irregularities in the trend that we will discuss shortly. Number 2. Within each column or group of the table, the ionization energy generally decreases with atomic number. For example, the ionization energies of the noble gases are in order of helium is greater than neon is greater than argon, krypton, and xenon. Number 3. The S and P block elements show a larger range of values of I1 than do the transition metal elements. Generally, the ionization energies of the transition metals increase slowly as we proceed from left to right in the period. The F block metals, which are shown in figure 711, also show only a small variation in the values of I1. The periodic trends in the first ionization energies of the S, P, and P block elements are further illustrated in figure 712. Figure 7.11, first ionization energy versus atomic number. The red dots mark the beginning of a period, alkali metals, and the blue dots mark the end of a period, noble gases, and the black dots indicate S and P block elements, while green dots are used to represent the transition metals. In general, smaller atoms have higher ionization energies. The same factors that influence atomic size also influence ionization energies. The energy needed to remove an electron from the outermost occupied shell depends on both the effective nuclear charge and the average distance of the electron from the nucleus. Either increasing the effective nuclear charge or decreasing the distance from the nucleus increases the attraction between the electron and the nucleus. As this attraction increases, it becomes more difficult to remove the electron, and thus the ionization energy increases. As we move across a period, there is both an increase in the effective nuclear charge and a decrease in the atomic radius, causing the ionization energy to increase. As we move down a column, however, the atomic radius increases, while the effective nuclear charge increases rather gradually. Thus, the attraction between the nucleus and the electron decreases, causing the ionization energy to decrease. The irregularities within a given row are somewhat subtler but still readily explained. For example, the decrease in ionization energies from beryllium to boron, shown in figures 7, 11, and 12, occurs because the third valence electron of boron must occupy the 2p subshell, which is empty for beryllium. Recall that as we discussed earlier, the 2p subshell is at a higher energy level than the 2s subshell. The decrease in ionization energy when moving from nitrogen to oxygen is because of the repulsion of the paired electrons in the p4 configuration as shown in figure 713. Remember that according to Hund's law, each electron in p3 configuration resides in a different p orbital which minimizes the electron-electron repulsion among the three 2p electrons. Electron configuration of ions. When electrons are removed from an atom to form a cation, they always removed first from the occupied orbitals having the largest principal quantum number n. For example, when one electron is removed from a lithium atom, it is the 2s1 electron that's removed. Likewise, when two electrons are removed from iron, it's the 4s2 electrons that are the ones that are removed. If an additional electron is removed, forming Fe3+, it now comes from a 3d orbital because all the orbitals with n equals 4 are empty. It may seem odd that the 4s electrons are removed before the 3d electrons in forming transition metal cations. After all, the writing electron configuration, we added the 4s electrons before the 3d ones. In writing electron configurations for atoms, however, we're going through an imaginary process in which we move through the periodic table from one element to another. In doing so, we are adding both an electron to an orbital and a proton to the nucleus to change the identity of the element. In ionization, we do not reverse this process because no protons are being removed. If there is more than one occupied subshell for a given value of n, the electrons are first removed from the orbital with the highest value of L. For example, a 10 atom loses its 5p electrons before it loses its 5s electrons. When electrons are added to form an ion to form an anion, they are added to the empty or partially filled orbital having the lowest value of n. For example, when an electron is added to fluorine atom to form the fluoride ion, the electron goes into one of the remaining vacancy of the 2p subshell.